Hello, this is a summary of moments, and moments are simply turning forces. So when a force acts on an object and causes it to rotate, we call that the moment of the force. And they're pretty intuitive. If you imagine, say, holding something, so I've got two lovely pictures here. This is meant to be a hand, sorry. And you're holding a rod here with a weight hanging on the end. Now, if I've got the same weight hanging on these two rods, this one, because it's further away from your hand, will create a bigger turning force or bigger moment than this one. And that leads us to this idea that the moment or turning force is linked to the distance the force is from the pivot and the size of the force. Because obviously if I put a bigger weight on here, the force would be bigger. So from that, we get our definition of a moment. And the moment is the force times the perpendicular distance from the pivot. And we'll talk about this perpendicular distance bit in a minute. But first of all, just conventionally, we would write that as m for moment equals force times distance. But sometimes it will be a d, sometimes it will be an x. It's not that important. So just a simple example, and then something interesting that comes from it would be this little case here. This little triangle I'm using to represent the pivot, or the fulcrum, you sometimes would say. In this example, the distance is 10 meters and the force is acting 20 newtons from that pivot. And actually, this is worth considering, this perpendicular distance here, because this force is acting straight down at the moment, and it is at 90 degrees to that lever. So the perpendicular distance between this force and the pivot is 10 meters. So there's nothing weird to do. So if I were to calculate this, I would just, being a good student, write down the equation. That's going to be 20 times 10, obviously, equals 200. And then the unit, well, newtons, meters, so Newton meters. And that should surprise some people because that looks like it's the same as a joule. If you think about a joule is force times distance for work done, a Newton meter as well, but it's a scalar quantity. This is not a joule because it is still a vector quantity. It has direction. You can go clockwise or anti-clockwise. Now, most of the things that you encounter will just be like this. You just multiply a distance and a force together. But at times, they'll introduce an angle. And I'll sort of give an example down here. So if you see an angle, I'm going to just slide this up slightly. We're going to have to take into account this perpendicular distance. So look at this example down here. I've got a lever 10 meters long, and I'm pulling up with a force at 20 newtons, but the 20 newtons isn't straight up. I'm pulling at an angle. And if you think about it, I'm pulling a bit to the right and a bit up, and the resultant is 20 newtons. And if you were thinking about, lifting something up in the garden using a plank of wood, and if you didn't pull straight up, it would seem more difficult to lift the object. And that's because the perpendicular distance of this force to the pivot is actually less than 10 meters. Really, when we say perpendicular distance, we mean the perpendicular distance from the line of action of the force, which is a complicated way of just saying a line along which the force acts. So in this case here, this dotted line is the line of action of the force. So if I wanted to find the perpendicular distance, I would probably just use a ruler and a protractor, and I would draw in a line that's at right angles to that line of action of the force. And then I would just measure this distance here with a ruler. And if it was a scale drawing, I could use that distance multiplied by the 20 newtons, and that would tell me the moment of the force. But I don't like doing this. I find it very complicated, quite confusing, and I think there's a simpler way of approaching these. So I'm going to redo this, but a slightly different way. And here we go. So the alternate method is to, instead of trying to work out the distance between the force and the pivot, I'm going to mark a distance on here just for completeness. What we could do is go back to thinking that this vector here could be resolved into two components. A horizontal component, which if you think about it, that's just pulling in this direction. That's not trying to turn this lever at all. And a vertical component. So if we find the vertical component of this 20 Newton force, that's acting at right angles to this 10 metre lever. Multiply those two quantities together and that will tell you your moment. So as an example, and I do realise that that is definitely not 60 degrees. My scale drawing is pretty poor here. But if I take that triangle there, or consider it as a triangle, the vertical component, I'll redraw this as a triangle just for completeness. If that's 60 degrees and that's 20 newtons, this will be sine. Okay, so this vertical component would be 20 sine 60. So this whole thing will simply become, if I redraw it, 10 meters along there, and then multiply that by the vertical component of the 20 Newton force, 20 sine 60, and I think, I worked that out already, that comes out at 17.3 newtons, and therefore the moment equals 10 meters times 17.3, 173 Newton meters. And that's about as complicated as these get. Okay. Now, the next thing is to think about what sort of questions you're going to get on the exam. And they're either going to be about equilibrium or about the principle of moments. So we're going to look at that next. Okay, starting with equilibrium. I've got two rods here. And I am going to have a force upwards on this rod and a force downwards on this rod, and I think we'd happily say that would be in equilibrium. The force upwards equals the force downwards, they cancel out, there's no net force, or sometimes we would say there is no resultant force on that rod. So this is in equilibrium. Now if I use the same two forces on this second rod, but I place one over here and one over here, we still meet the condition that there is no resultant force. The force upwards cancels out with the force downwards, zero resultant force. But this clearly is not in equilibrium. This is going to rotate. So it turns out there is a second condition for things being in equilibrium. There has to be no resultant force, but there also has to be no resultant moment. So that one's not in equilibrium. So no resultant force and no resultant moment. Or sometimes you would say no net turning force. Okay, right. Pretty much everything else you'll do with moments will be to do with the principle of moments. There's the principle of moments. And the principle of moments simply states, for an object in equilibrium, the sum of the clockwise moments about a point, and that's something that's included in mark schemes and often underlined, equals the sum of anti-clockwise moments about that same point. Now this is important, it's something that's missed a lot. Most people would just write these first two bits, sum of clockwise moments equals sum of anti-clockwise moments. And that's true, but at A level you'll often have to decide where you're actually going to take moments about. You have to choose to use the same point every single time. So, bear with me 1 second. So, how do you do these? Well, there's a couple of little tips for when you do this. Tip number 1. You might not feel like doing it, but redraw a free body diagram. If you draw the free body diagram, it often makes it clearer. If you just annotate over the picture in the exam paper, sometimes it can get a little bit confusing. 2, choose an appropriate point to take moments about. Sometimes you'll have to do that about 1 point, sometimes about 2 different points in a particular question. Basically, the idea is that if you've got 2 unknown forces, if you take a moment about the location of one of those unknowns, it doesn't contribute to the moment. And therefore it disappears from your equation and you can find out the other unknown thing. And the third thing is sometimes you may be tempted to make questions more complicated than you need to. Often you can find one unknown force in a question using moments, but the second force you can just use by resolving forces. And I'm going to put a worked example together for the next video. Okay, thank you.